Great. Okay. Hello. I'm Tobias, and together with my colleague Bingyi, I will now discuss the Landmark Retrieval Challenge. This year, we held the third edition of the Landmark Retrieval Challenge on Kaggle, which just ended 2 weeks ago. And we also have a recognition challenge that is still ongoing and that we're going to discuss in the next session of the workshop, the afternoon one. So compared to last year, we had a significant increase in the number of teams. We were happy to have like 540 participants. Also we were happy that we were able to again provide $25,000 in prize money, which was shared between the top 3 winning teams. And most notably this year, we actually went for a completely different format of the challenge, but more details on this later. Let me first introduce the general task. Basically, given an image, retrieve images from an index that show the same landmark. So for example, here for the 4 images on the left, you're supposed to retrieve the images that have the same color of frame. So as it's common in image retrieval, we use the mean average precision metric, which is cut off at the top 100 retrieved images. Apologies. Okay. So how was our challenge data structured? So we basically had 2 parts. There was a public training data set for which we used the Google Landmarks dataset v2 clean. So this is a subset of the Google Landmarks dataset v2 that was cleaned up by the winning team from last year's challenge. Also cited here. So thanks again for providing this dataset for the challenge. And also we had evaluation data, which consisted of both an index set and a test set that we collected newly for this challenge. And these sets share similar characteristics to the original Google Landmarks dataset v2, as we wanted to preserve the same types of challenges that this dataset presents. And I'm going to go into a bit of detail on these now. So one particular challenge is that there's a very long-tailed class distribution, which kind of naturally emerges when you crowdsource image data. There's a few, like relatively small amount of landmarks that have a very, very large number of images, like the ones you see here on the on the left side of the figure, and a very, very large number of landmarks that are maybe lesser known and more local, that have only a few images in the data set. And obviously this makes training and retrieval rather tricky. And another important challenge that we have is matching, which is like generally the topic of research in image retrieval. So how can we match images that have different perspectives, different lighting conditions? There are occlusions. And if you look at the bottom row, the 3rd and 4th images are interesting here because the 3rd one is actually a painting that needs to be matched against the query, and the 4th one is a historical, or actually the 4th, 5th, and 6th one are all historical photos. So these images here, I should mention on the slide, are actually from the original Google Landmarks dataset v2, but the same kind of challenges exist in our competition. And so finally, about challenges, there's also a lot of intra-class variability. So basically, because people take photos from all over the landmark, there can be total views of the place, there can be details of architectural details, sorry, inside and outside views of the place, and so on. Bit of an advertisement. So if you want the full Google Landmarks dataset v2, is available here on GitHub. So if you want to use it for your own instance level retrieval research, image retrieval, or just want to train a landmark embedding, feel free to use it. And also, actually this year, we just launched a new visual browser for the dataset where you can click on a country and then explore the places there or search for specific places and see what images exist in the data for this place. Okay, so before going into this year's challenge, I want to talk a little bit about last year's challenge. The reason is that I want to motivate some of the choices that we made for this year. So if you wanted to participate in the challenge last year, you would first download the dataset, so the train, test, and index images. And you could train your models, you could run some pre-processing like database augmentation, and then you could run a retrieval on your own machine or whatever hardware is available and produce a ranking. So for each test image, rank the index images with respect to their relevance, and then write this ranking into a CSV file that you then upload to Kaggle. And Kaggle uses the private ground truth to create a score and put you on a leaderboard. Here's the top solutions from last year, so the top 3 teams. I'm not going to go into too much detail about them, but just wanted to note that they all made rather heavy use of ensembles. They used several models that basically were kind of concatenated or averaged. Usually people use the combination of local and global features and some clever forms of online re-ranking, query expansion, or other methods. And yeah, so a few takeaways from the challenge last year. So on the positive side, we were really happy to see some very healthy competition that unfolded last year. Yeah, there was quite a high diversity of approaches that were presented, and even some publications followed from the challenge. On the other hand, we felt that a lot of the high-performing approaches were also rather computationally expensive and complex, which may not make them as useful in practice. And also, there was some advantage to teams that had more computational power, because basically they could run more experiments, train more models. And importantly, there was some potential for cheating in last year's challenge. And because the Google Landmarks dataset is mostly collected from Wikimedia Commons, it's actually possible to mine Wikimedia Commons, just download all the sites and get the metadata for these images, and then you could figure out the landmark labels, or could figure out which of the test images were landmarks or not. And that actually happened last year. So the winner, or the original winner of the challenge, was actually found out to have mined Wikimedia Commons, which was against the rules, and so we had to disqualify them. And so we hope that we can prevent this this year. Okay, so now here are our motivations for this year's challenge. So first of all, we wanted to put a bit more focus on efficient and more simple solutions. Then we felt that because there was already quite some headway made into improving baselines and achieving pretty good mean average precision scores, we wanted to kind of raise the bar a little bit and introduce some new challenge. And then third, as I mentioned, we wanted to reduce the risk of cheating. And for the first two, we decided to standardize the runtime environment. And again, we're gonna go into detail later what that means. And for reducing cheating, we decided to keep the test and index data private, while last year they were able to be downloaded. And so basically, the gist of this year's format is, instead of uploading a CSV file with your predictions or with your rank list, you would upload a TensorFlow model that extracts an image embedding, and we would then run the retrieval and scoring on the server side. And I will now hand it over to my colleague Bingyi, who will explain this in detail.
Thanks, Tobias. So, as Tobias mentioned, this year our challenge has a new format. So let's now move on to discuss the corresponding new submission process. So here we're going to show a flowchart for the participants. They can use any public data to train their embedding model and evaluate the model. And once they're happy with the model, they can export and submit the model to the Kaggle server. Tobias, next, please. So here, the blue block shows what was going on the Kaggle server. So on the Kaggle server, using the model uploaded by the participants, it's going to extract the embeddings on the private data for both index image and test image. Afterwards, compute pairwise similarities, then rank the index image. Afterwards, it performs retrieval. So in the end, it's going to compute the metrics for this retrieval solution using the private ground truth on the Kaggle virtual machine. So here, for the retrieval task, the score mean average precision will just get computed and then upload to the leaderboard. So because of the new format, we also have the resource constraints. Here it shows for each Kaggle virtual machine, we have a NVIDIA Tesla P100 GPU available, and then 2 CPUs along with a RAM which is 13 gigabytes. Also, there is no Wi-Fi. As mentioned before, we also have the computation time constraints here. So for each submission, the maximum computation time is 9 hours. Each team allowed to submit maximum 5 submissions per 24 hours. So because of the new format and also the resource constraints, we feel our challenge may have a high barrier of entry. So to make your life easier, we decide to release the baseline model. So it's a ready-to-submit model. It's just the model which we present in our GLD V2 paper at CVPR this year. So as shown on the right side, it's a ResNet 101 embedding, leveraging arc phase loss and gene pooling, which use the GLD V2 clean to train the model. We also release the source code for training and exporting a model. We hope this baseline model actually make your experience with this challenge more pleasant. So next, please. So after talked about the submission pipeline, now let's move on to talk about this year's challenge data. Last year, we released the Google Landmarks Dataset V2, so all the ground truths are fully public. So we were no longer able to run a challenge on that anymore. We need to collect the new data. And also, due to the new format, we have some limit resource for the submission kernel. So we have to limit the amount of the test data and also the index data. Now let's move on to discuss about more details about this year's challenge data. There are two parts of the challenge data. On the left side, we call it a development data. So here, the development data that will be available to all the participants. And on the right side, it's evaluation data. For the evaluation data, so it won't be public to all the participants. It's only available on the Kaggle server. Now, we're going to discuss more details about this development data and evaluation data. For the development data, we have a training set. It's GLDV2 Train Clean. It contains 1.5 million images of 81K landmarks. There is no need to re-download this data. It's available there on the Kaggle server. And there is index data, which is 76K image from the GLDV2 index. Also, we have test set. Tobias, next, please. So the test set has 1.1K landmark queries from GLDV2 test. So here we have to emphasize for the index set and the test set from the development data, they're not really used for any scoring. So they're just going to mimic the evaluation data because the participants has no access to the evaluation data. So now for the evaluation data, we have an index set which contains 100K image from Wikimedia. There is no image overlap with the GLDV2. There are partial class overlap with GLDV2 train. So here, partially class overlap because we also want to test the journalism of your model. And for the test set from the evaluation data, there are 1.6K landmark images collected for crowdsourcing. So we split them to the public leaderboard and private leaderboard. For the public leaderboard, it's just when you submit your model and the Kaggle virtual machine is going to compute and upload the score. That's the score for the public leaderboard. For the private leaderboard, so you won't release until the end of the challenge. So here, we split the landmark images. 33% of them went to the public leaderboard, and we reserve 67% of them for the private leaderboard. So after discussed about the submission pipeline and also the challenge data, now let's move to discuss about the final results for this landmark retrieval task. So in total, we have 540 teams participating, and here we show the results from the private leaderboard. We list all the top 10 teams along with our baseline. So here we could see the last row on the right table is our baseline colored in green. So the rank is 252 with a MAP of 24.38%. So we're happy to see there are over 250 teams with our baseline. And we can see all these top 10 teams, they scored over 30%. For the first two teams, the Kitar and BYSJ team, they managed to score over 36% as a mean average precision, so which distinguished themselves from the other winning teams. So it's our honor here to have these three teams which are colored in orange to give a presentation in the following session to share their solutions with us. So they're the GITA team, the BYSJ team, and Open Neural Network Exchange team. So for some of these teams, so here we also plot the score histogram for all the participants. So we could see here the red dot, which is the baseline. For the orange bar, which is on the left side of this baseline, there are 290 teams. They're the teams didn't score better than the baseline. They're either have a lower MAP or equal MAP as the baseline. And on the right side, there are the teams with a higher score than our baseline. So we can see there are 223 teams. They managed to get a higher score than the baseline, but still lower than 26%. There are 28 teams on the right side. They managed to get a MAP of over 28%. So we have a quite strong baseline. It's pretty impressive. These teams actually scored much better than the baseline, like they beat the baseline than a large margin. So the next one, please. For the teams, they share their model with us. We were able to run more metrics on their model. So if you're one of the winning teams and you want to get a more comprehensive understanding of your model, feel free to just share the model with us. We're going to run more metrics. So here, it's just the precision by rank curve. We choose 4 teams along with our baseline. So from here, we could see our baseline is the purple one. So for the baseline on the very left side, so we have a mean precision of less than 50% at rank 1. And then for the first winning team, they managed to score over 60 at rank 1 for the mean precision. So in the next slides, we're going to show more metrics. So here, besides the MAP score, we also showed the other metrics such as the mean position. The mean position here is the second last column, which means the mean position of the first relevant image. So we could see our baseline, which is also colored in green. The mean position is over 32. And for the first team, they managed to get a mean position, which is below 18. So this number, the smaller the model is performing better. And also, we showed a precision at rank 10 on the very last column. It's just as one dot on our curve. So for our baseline, the score is like 30.31%. And for the first team, they managed to get something better than 42. So we could see all these teams, they beat the baseline. They're performing quite well. So the next one, please. So besides compute more metrics, we also conclude some top performing techniques for this retrieval challenge. For the architecture, EfficientNet and ResNet seems to be the most popular backbones, and we want to encourage all the teams to submit embedding-based model, and we saw almost every team use the CNN-based global features. Many teams leveraging gene pooling, and we're happy to see there are one or two teams, they're using the dog architecture, which we proposed in our ECCV paper this year. There are varieties of laws get used, like Farquhar laws, arc-phase laws, cos-phase laws. And interesting, we were not able to stop you guys from being using in-symboling, so even with the resource constraints. Besides in-symboling, there are other techniques like data augmentation, transfer learning, progressively resizing has been widely used. For the dataset, many teams use the GLDV2 clean to train their model. We also see some like really strong performing team, they use the GLDV2 full. And some of these teams use the GLDV2 original dataset, but they did some recleaning themselves. So we will be happy to have them to talk about their dataset they're using for their method solution in the following session. So before we move to the Q&A session, we would like to summarize this landmark retrieval challenge. So this year, we use a new format. We encourage embedding model submission. We want the participants to focus on improving global features. So this new format has the computation and time constraints, which has a high barrier of this entry for this challenge. But luckily, we have 540 teams participate 5 times more as last year. There are over 400 teams with more than one submission. We also see a lot of interesting sharing and actively discussion about this retrieval challenge. So it's the first year we use this new format. We're very curious to see your constructively feedback about this. We saw some people, they want to use other frame rather than TensorFlow to train their models. We saw the discussion about this. Some teams were able to convert their model from the other frame to TensorFlow. And we also see some teams want to use more advanced method like global plus local features and also special verification, but it was not possible due to the resource constraints. So we're going to take all of this into serious consideration when we try to prepare next year's challenge. And to conclude, we're very happy to see. So our winner actually achieved over 58% relative improvement over a very strong baseline. So now we're happy to take questions. So I can take questions with Tobias. So
yeah, there are some questions in the Q&A. So maybe Tobias and Bingyi, you can go over those.
Yeah. So first, let me start by saying, so there is also going. We have only little time, so if there are more questions, we are going to have more time for Q&A in the session after the session that discusses the recognition challenge. So we can make this as a Q&A for both challenges. But I see one question from Tony Ing who asks, in the Google Landmarks Dataset V2 paper, there's a disproportionately high amount of images or of landmarks from Europe, for example, churches, while there are little landmarks from Asia or Africa, for example, monasteries. And he's curious if this distribution is seen across both training and test set, and if we have considered in future challenges to have some sort of region-based categories. Okay, yes, so we are definitely very aware of this. This is one of the weak spots of collecting the data from Wikimedia Commons, because the communities of this site are most active in Europe and then second most active in the US. So this definitely perturbs the kind of world that this data set represents towards these regions. And we hope that we can make some progress with this. And actually, the this aspect is already better in the V2 of the dataset versus V1, which was very US and Europe centric. But we can still improve this further. As for the training and test sets, kind of. So the test set was not collected from Wikimedia Commons entirely, but we used crowdsourcing for that. And so there, I mean, so let's say a different kind of crowdsourcing, but similar biases exist there, although we definitely had some more coverage in Asia. Yeah, so this is definitely something you want to improve. As for the region-based categories, that's actually an interesting idea. So thanks for that. We'll think about that. Okay, that's all the questions we have for now. You're welcome. Yeah, I think since we are already at the end of the time.
I had a quick question, Tobias. If you go back to these performance pages, which more about like the mean position and also the precision at 10. And there's one interesting thing I observed is that we have like precision at time of like 40% something, while we have the mean precision of 17, which does it mean that you either have like a very high precision category, or we just didn't do anything at all, which means most of the images are ranked like over like about 100, and then we get like about 100 something, and then we calculate the average, we get like 70 something. Is that true?
Oh, do you know that, Andre?
I think, Shu, to answer your question, the mean position ends up being very biased because for the queries where there are no relevant retrieved images, since we only look at the top 100 images, to compute this metric, it just artificially assumed that, you know, the team retrieved a correct image at position 101. So it ends up being dragged much later into the, you know, if we calculated the median, probably would be much lower, as you can imagine.
I see.
Yeah, does that make sense?